Yo, we're back with Freestyle Physics covering one of my favorite topics of all time, conservation of mechanical energy, featuring the master equation of mechanical energy conservation. Let's get this rolling. Here we go. I'm calling out to the Lake Nation. It's time to learn energy conservation. It's so much easier than the laws of Newton, cause you don't need to do no vector computing. So if you have a choice of how to attack, energy is definitely the easier track, since energy and work, they both are scalars. Using them, you'll never be a failure. In fact, you'll be a physics superhero if you remember to set locations of zero or potential energy, which can be anywhere. On the ground or in the air, since potential energy, it's always relative. It can be positive or it can be negative. It's up to you to realize the dangers. With PE, all that matters is the changes. The one exception I'll spit to these drums is that with springs, they should be zeroed at equilibrium. Now, potential and kinetic, this is no bull, are energy forms that are called mechanical. And though energy can't be destroyed or created, it can be transformed, then dissipated into non-mechanical forms like heat and sound. And those forms, they just don't stick around. From total mechanical, you can take or give using work that's non-conservative. The key to all these transformations are one equation to rule them all, the master equation. Let's start off with a few points about mechanical energy. There's only really two fundamental forms of mechanical energy: kinetic energy, energy of motion. We use the equation K equals 1/2 mv squared for that, as derived last chapter. And besides that, there's just potential energy. Now, yeah, there are a lot of subforms of potential energy, but they all have a few things in common. They're only associated with conservative forces. For example, gravity, the spring force, the electric force. Systems of objects actually have potential energy. In other words, a barbell, which is totally isolated in its own universe, cannot have potential energy. But the Earth barbell system, together those two objects in that system, can have potential energy. Only changes in potential energy are meaningful, though you can assign potential energy equal to 0 at some arbitrary point in space. Doesn't have to be the ground either. Sometimes we can assign it at infinity even. But we assign some arbitrary point to 0 potential energy, and then we can assign specific values of potential energy to other points in space. Basically, how potential energy is defined is this: the gain in potential energy of an object or a system as you move that object from one point to another is the opposite of the work done by the conservative force during that trip. In other words, delta U is negative work done by the conservative force. For example, as I lift this calculator, gravity's doing negative work, and the change in gravitational potential energy of the calculator Earth system is positive, that same amount of work, because I can get that exact amount of energy back as kinetic energy just by letting it go and letting it return to the same place that started. With calculus, the way we express that is delta U is equal to the negative of the integral of f dotted on dr. In other words, that is the opposite of the work done by the conservative force as it followed that path. Important to recognize are some forms of energy that are not considered mechanical energy. Thermal energy is not considered mechanical energy, even though it's really kinetic energy of individual molecules. Energy tends to leave systems in this form, and a lot of times when negative, non-conservative work is done, some of the energy is transformed into thermal energy. It's just molecules moving fast, but we don't count that as kinetic energy. We only count the bulk motion of an entire object as kinetic energy. Sound, also not a form of mechanical energy, also tends to be dissipative, just energy tends to leave systems with sound. Chemical energy, nuclear energy, and mass, as in E equals mc squared, also not considered mechanical energy. This may in fact be the shortest lecture of all time, because I could actually complete this lecture in about 10 seconds. It all comes down to understanding and properly using one equation, which I call the master equation for mechanical energy conservation. From time to time, we have one equation so powerful that you can pretty much use it for every single problem in a topic. And this is one of those times. The master equation for mechanical energy conservation is E initial plus work non-conservative equals E final. Here, E represents mechanical energy. Not all energy, but mechanical energy. And those different types of mechanical energy include, for example, kinetic energy, spring potential energy, gravitational potential energy, and also electric potential energy, but we're not going to deal with that until next semester. So let's get on with this. The lecture is done. Now, all I've got to show you is several applications of this and how to actually solve these problems with this master equation. And there are a couple of tricks that you're going to want to take advantage of.